So we were doing complex numbers, the last topic for the semester, and we did arithmetic with complex numbers. This time we want to do powers and roots in particular, and the way we do that is using the polar form of a complex number. We said every complex number, by definition, is a real number a plus square root minus 1 times another real number. We call those complex numbers. If b is 0, we said it's a real number, so the real numbers are actually a subset of the complex numbers. And if a is 0, then it's called a pure imaginary number. And from that, we then constructed the complex plane. In fact, I prefer to do it this way. Z equals x plus I, y. I'll match my notation a little better today. So if I put this as x and y, any point I plot here at x along the x-axis and y along the y-axis represents the complex number x plus I, y. Just like each point on the real number line represents the appropriate real number, each point in this complex plane represents the complex number you get by dropping these two perpendiculars and seeing what the numbers are. Then we said what's really useful for doing lots of computations, we're going to find particularly for doing powers and roots, right? We did arithmetic last time, addition, subtraction, multiplication, division. Now we want to do powers and roots. This polar form is really useful where we said we're going to do this. It's like polar coordinates in the Cartesian xy plane, not the complex plane. We can take this angle and standard position, call it theta, that goes to the point, and this distance from the origin r, and compute r theta coordinates. And in that case, the imaginary number can be written as z equals r cosine theta plus I sine theta. We call that its polar form. I'll call that equation 1. Why is that so? It's because if you just multiply this out, this is equal to r cosine theta plus I r sine theta. That's just by multiplying out this times this plus this times this. And this from polar coordinates is x, right? If you drop the perpendicular here, x over r is cosine theta, right? So cosine theta is x is equal to r cosine theta, right? From the triangle, x over r is cosine theta. Adjacent over hypotenuse, and it works in all quadrants, but I just draw it in the first. Then you multiply by r and get this one. And then similarly over here, y over r is sine theta, opposite over hypotenuse, and so it follows that y is r sine theta. We did this in polar coordinates before. Now, if you just multiply this out, this is x plus iy. When we write it, and so these two are just two different ways of writing the complex number. This we call the standard form or the rectangular form. But if we write it in this fashion as r cosine theta plus I sine theta, where theta is the angle and r is the distance from the origin, we'll call that the polar form. And unlike polar coordinates that we did in the Cartesian real plane, r cannot be negative here. We're going to make always for complex numbers, r is equal to the square root of x squared plus y squared, not plus or minus. We'll only take the positive value of r. And tangent theta equals y over x will apply when x isn't equal to 0. And since we're picking r greater than 0, remember we have to pick theta into the same quadrant as the point. Right? We can do polar coordinates before r positive and theta in the same quadrant, or r negative and theta in the opposite quadrant. Since r is positive, theta will also always be the quadrant of x, y. Or since we're doing complex numbers, we'll call it x plus I, y. Theta into that quadrant. And then if x is equal to 0, then you just look at it to figure out what the angle is. All right. Look at the picture. If the point is up here, then you say, oh, theta is pi over 2. if x is 0 and you got a point down here, you say, oh, theta is 3 pi over 2, right? So that was the polar form, was to write this one. And then there was a short notation. This gets cumbersome to write. R cosine theta plus I sine theta. We can also write it as Z equals R psi theta. Cosine plus I sine theta, abbreviated. And we said that number E from algebra, 2.718 approximately. You can also write it as e to the I theta. You don't find that out till calculus, but it turns out to be e to an imaginary unit times a real number. Comes out to be cosine plus I sine. And I forgot my R here. So you'll see both these notations. This one we won't use. It's for when you do calculus. But this one makes a nice abbreviation for us. They all mean the same thing. R cosine theta plus I sine theta. Any questions so far? Does that look familiar from a long time ago now? Now, this has a really neat geometric interpretation for multiplication, division, powers, and roots. Suppose I take Z, the product of two complex numbers, Z1 and Z2, with Z1 and Z2 written in their polar forms. So Z1 is some distance from the origin, R1, times cosine plus I sine theta 1. And that'll be Z1. And then Z2 will be R2 times cosine theta 2 plus I sine theta 2. What happens when we multiply these? Well, Z, the product of these two numbers, is now, well, this times this, R1 cosine theta 1 plus I sine theta 1 times R2 cosine theta 2 plus I sine theta 2. And you can multiply in any order, so I'll put the R1 and R2 first, and then I'll multiply these afterwards. This is theta 1 here. Now what we get then is R1, R2 times, let's see, well, cosine, cosine, plus I cosine sine, sine theta 1, sine theta 2. That's first outside, and then inside is I times sine theta 1, cosine theta 2. This one times this one with an I. And then plus last, this times this. Well, I squared is minus 1, so it's minus sine sine. There it is. So this is a FOIL of these two things, and then R1, R2 out front. Now, what is this in here? Cosine, cosine, minus sine, sine. Where did we see that before? Remember? Back to test 3, right? Cosine, cosine, minus sine, sine is the sum formula for cosine. This is cosine theta 1 plus theta 2 is cosine, cosine, minus sine, sine. And how about this one? Sine, cosine plus cosine, sine, multiplying I, is sine, cosine plus cosine, sine. That's the sine of the sum of angles, right? Sine of theta 1 plus theta 2. there it is. This is a neat theorem that says when you multiply two numbers, the polar form of the zone, look what this is. This is a number, so I can call that R, times cosine of an angle theta, plus I sine of an angle theta. This must be the polar form of Z, the product of Z1 and Z2. This is its R, this is its theta. And evidently, when you multiply two complex numbers, their polar form, but whatever form, but the polar form shows that the new R is the product of the distances of the two numbers from the origin complex plane, and the new angle is the sum of the two angles. So it has a geometric picture that looks like this when you multiply complex numbers. Here's Z1. It has some distance from the origin R1 and some angle theta1, right? Here's Z2, some other number in the complex x plus iy plane. And it has this angle, theta2, and this distance R2. So what is product Z1 times Z2? It has the angle that's the sum of the two angles, and the distance is the product of the two distances. So it's this distance times this distance far out. Maybe this is R1 times R2 is R, the distance from the origin here. And the angle here is just this one tacked on to the other one. So the angles add and the distances multiply. That's what that says. This is the picture, and it constitutes a theorem that the product of any two complex numbers, which is proved, Z1 times Z2 has polar form R1, R2, cosine plus I sine, I'll write an abbreviation, SICE, the sum of the angles. So the angles add and the distances multiply. We can call that formula 2, actually. So polar representation makes kind of a neat, simple way of thinking about multiplications. We'll get an example now because I haven't even done a review of polar form. Let's try a couple of examples off the homework here. See when you do the homework if this lines up with what you do. Find the polar form of the complex number whose standard form is minus a half I. Suppose that's my Z. Well, number without the I we call X, and the number with the I we call Y. So I can find this by simply using the two equations. R equals square root X squared plus Y squared. Well, it's a fourth plus a fourth, a half. Square root is 1 over square root 2. There we go. So this point is 1 over square root 2 units from the origin. If you were to plot it, you'd see that, right? I'm going in the complex x plus iy plane. And x and y are both minus a half. Right here, 1 over square root 2 units from the origin. That represents the complex number, minus a half I. Now, how about theta? We solve tangent theta equals y over x. It's minus a half, that's y, over x minus a half. Oh, it's just equal to 1. How do I solve tangent theta equal 1? I might have memorized it by now. actually two different directions, right? You have 45 degrees or 135 degrees, both have tangent equal to 1, the two opposite directions. The way you solve it, if you don't remember that, is you write that as tangent theta equals, and you rewrite this as 1 over 1, and root sum square these numbers. Right, it is a quotient, root sum square the numbers, get square root 2. Well, it's 1 over square root 2 over 1 over square root 2, or it can be minus these. Which one is it? I want my point to be in quadrant 3, so I have to choose the angle that goes into quadrant 3. Remember, for complex numbers, we're only using r positive and theta into the same quadrant as the point, so we need this one, not this one. We want quadrant 3. And on the unit circle, we can find that angle now. It goes through the point minus 1 over square root 2, minus 1 over square root 2, also known as square root 2 over 2, minus square root 2 over 2, minus square root 2 over 2. It's evidently 135 degrees, or 5 pi over 4. So theta equals 5 pi over 4. And we find, therefore, that the polar form is z equals r cosine theta plus I sine theta by equation 2, by 1, is, well, r was equal to 1 over square root 2, and theta was 5 pi over 4. There it is. There's the polar form of that complex number. And you use any coterminal angle too. You could use minus 3 pi over 4 if you prefer it. It would have the same cosine and sine and give you the same number. So you can write the number either as minus 1/2 I, or you can write it as 1 over square root 2 cosine 5 pi over 4 plus I sine 5 pi over 4. If you computed these angles and multiplied back, you'd get back minus 1/2 I. That's the idea. Just different ways of writing the same number. Suppose I convert from polar form to rectangular form. It's called standard form. Suppose I have this number, which is z equals 2 cosine pi over 3 plus I sine pi over 3. That's its polar form, right? That's the x plus iy form. All you have to do is compute the cosine and sine and multiply out. It's nothing more than that. From the unit circle, you can look at it and say, oh, pi over 3. I know what this is. This is 1/2 and square root 3 over 2. So the cosine is 1/2. Sine is square root 3 over 2. Right? And now 2 times 1/2 is 1. 2 times I square root 3 over 2 is I square root 3. Let's put square root 3 to I, actually. This polar form of the complex number is just another way of writing 1 plus square root 3i. All you have to do is evaluate cosine and sine and plug in. All right, so there's the rectangular form for the polar form. But now the polar form, we said, is really useful for doing geometric interpretations of things like products there that we just put down. For instance, now we have this problem. Find product z1 times z2 polar form if z1 in polar form is 2 square root 3 cosine 116 plus I sine 116 degrees. And Z2 is in polar form 2 cosine 82 degrees plus I sine 82 degrees. Suppose these are my two complex numbers in their polar form, R cosine plus I sine. What is their product? Instead of multiplying it out like we did before, right, foiling the actual, their rectangular forms, let's multiply them in polar form. By equation 2 that we had there, Z, the product of Z1 and Z2, is R1 times R2. Well, this is R1, whatever multiplies cosine plus I sine, and this is R2. And this must be theta 1, and this must be theta 2. So we have, remember, R1, R2, cosine plus I sine, I'll write it in abbreviated form, of theta 1 plus theta 2. The angles add and the r's multiply, is now 2 square root 3 times 2 times cosine plus I sine of 116 plus 82. In other words, we have 4 square root 3 times cosine plus I sine of 198 degrees. There it is. There's the polar form of the product. We just had to add the angles and multiply the distances. All right, does that make sense then? You can use your polar coordinates equations to convert complex numbers to have a polar form, and then you can multiply them by multiplying the r's and adding the angles. Very neat. And then you say similarly, you can probably guess this one. We won't prove this one, but it's a similar proof. So don't want to repeat it unnecessarily. It's just a little longer. Similarly, we have the following theorem for Z2 not 0, that is 0 plus 0i. Not that. Following theorem applies. Suppose I take Z1 divided by Z2. Can you imagine what happens this time? It's R1 over R2 times cosine plus I sine, the difference of the angles. You can see why immediately, if you think about it, how you could do the proof of this quickly, actually, using the multiplication theorem. If I have Z1 over Z2, suppose I want to multiply by Z2 to get Z1 back, right? I should be able to multiply by Z2 and get Z1 back. So I multiply this one by R1 psi theta 1, or excuse me, multiply by Z2 to get Z1 back. So I multiply this by R2 psi theta 1 minus theta 2. The R2 cancels the R2 down here. And then I have to add the theta to the angle, leaving psi theta 1. I get R1 psi theta 1. Sure enough, that's one way to prove it, is to just multiply this by Z2, and you see that you get Z1 back. But when you divide, then the r's divide and the angles subtract. You have this nice geometric interpretation of subtraction. Let's look at 5A off the homework. I think this is 4. This is 4A here. 5A says this. Suppose Z1 in polar form can be written this way. 21 cosine 135 plus I sine 135. And Z2 is 3 times cosine 65 degrees plus I sine 65 degrees. Then we'll call this 3 by equation 3. If you want to divide one by the other, you just divide the r's, you get 21 over 3, and you subtract the angles. Cosine plus I sine of the difference. One's 35 minus 65. So it's 7 cosine plus I sine of 70 degrees. There it is. How about that? It's easy to divide by subtracting angles and dividing R1 by R2. There's how polar coordinates are neat for multiplication and division interpretation. But they're actually very important for doing powers and roots, right? Last time we did arithmetic and Well, what if we need to do algebra, right? More generally in algebra, we need powers and roots. How can we do those? And now the polar form shines from equation 2 for the multiplications, right? We observe the following. We're going to apply it repeatedly. Suppose I take z times itself, so I've got z squared. What's its polar? What can we do to compute z squared in polar form? Well, it's r psi theta, r psi theta, if r psi theta is z. And now by the multiplication theorem, the r's multiply, so you get r squared, and the thetas add, you get psi theta plus theta, and so you get r squared psi 2 theta, right? Now you compute z cubed, right? That ought to be z squared times z. So it's this one, r squared psi 2 theta, times z is r psi theta. Right? And now the r's multiply, r squared times r is r cubed, and the angles add, 2 theta plus theta. We have, oh, maybe I should put it this way, r squared times r, and then r squared times r is r cubed, and this is psi 3 theta. You see the pattern, right? If you let z be r psi theta, that was assumed, the z squared is r squared psi 2 theta, z cubed is r cubed psi 3 theta, it follows, inductively we say, that z to the n is r to the n psi n theta. This one, the major result, which we'll call 4, called de Moivre's theorem. Well, it's pronounced lots of different ways. De Moivre's theorem is, look in the videos online, it's very funny. Everybody pronounces it different. De Moivre's theorem, de Moivre's theorem. Says to compute an nth power, you take the distance from the origin to the nth and multiply it by cosine plus I sine of n times the angle of the original number. So it has this picture geometrically. Suppose I take a complex number over here with some angle theta and some distance from the origin r. What does r squared look like? Well, let's start it closer here. Let's think z, this is z, r psi theta. Z squared then has double the angle, right? 2 theta, about like that. And the square of the distance from the origin. So if it's whatever, 1.5 units here, then this will be 2.25 units here, the square of 1.5. So this is r squared distance and 2 theta angle. If you want the cube, then you triple the angle. You go to about here, and you cube the original distance. So this is r cubed units from the origin, if this is r. And the angle is 3 theta, and so on. Right? That's de Moivre's theorem. For the nth power, you take n times the angle and the nth power of the distance from the origin. So very important geometric interpretation, but what's more, it means I can compute these things in an interesting way. Suppose I have this kind of thing. I want to take the number 1 plus I to the 14th power. Who can multiply 14 of these together, right? I'd probably make a mistake. But if I put it in polar form, I can compute it pretty readily here. And it's not short, but I compute it more carefully. What is the polar form of this complex number? I need to convert it, right? I have 1 plus I. I don't need to draw this, let's say. Then I compute R is the square root of x squared plus y squared. Think of it as 1 plus 1 times I. So it's square root of 1 squared plus 1 squared is square root 2. At this point, yeah, I do need to draw it. Here's 1 and I, and here's 1 plus I. Is square root 2 units from the origin in the complex x plus iy plane. And now what's its angle? You can probably figure it by looking. Tangent theta is 1 over 1, y over x, which you then convert to 1 over square root 2 over 1 over square root 2 by dividing this by root some square of 1 and 1. Well, once you figure on the unit circle, is the angle right here, 45 degrees. Oh yeah, we've probably seen that a million times, right? But there's the derivation just in case. You could use the arc tangent if it was one, not a special angle here, right? This is in the first quadrant. So theta is equal to pi over 4. R is equal to square root 2. And we can rewrite this as 1 plus I. R cosine plus I sine theta is square root 2 times psi pi over 4. So this is the polar form. I'm just computing on this on the side. Then I'll plug it in over here and just rewrite this as square root 2 psi pi over 4. I could compute cosine and sine and get this back. What's the 14th power? By de Moivre's theorem, right? I take the 14th power of R and 14 times the angle. So this is this is my R and my theta. This is 14th power square root 2 times cosine plus I sine of 14 times the angle pi over 4. There it is. Well, let's see. Square root of 2 to the 14th is 2 to the 7th. Right? 2 to the 1/2 to the 14th is 2 to the 7th. And this is cosine plus I sine of 7 pi over 2. Well, 6 pi over 2 would be, here's a hint. The cosine and sine of 7 pi over 2 is the same as any coterminal angle. All right. So because this is 2 pi is 4 pi over 2, we could equally well write this as 2 to the 7th, which is 128. And we could write 7, instead of 7 pi over 2, we could write 3 pi over 2, because I just subtracted 2 pi from it. This is a coterminal angle. So I can always change it to a coterminal angle because cosine and sine will be the same. Now I can deal with it better. I can run it over here. This is 128 cosine pi over 2 plus I sine pi over 2. This is its polar form. That's good. But I can also find its rectangular form, right? If I just compute cosine and sine, cosine of pi over 2 is 0. That's 3 pi over 2. I'm sorry, 3 pi. Cosine of 3 pi over 2 is 0, and sine of 3 pi over 2 is -1. You remember from the unit circle, right? It's the angle down here. And so actually this number is minus 128i. Simpler to write it this way than its polar form. So here's the rectangular form. But there it is. I don't have to multiply 14 of those together. I can just multiply the angle by 14 and take the 14th power on my calculator or whatever of square root 2, and I come up with this number. How about that? So now you see the power of the polar form is you can compute powers of numbers handily with the Demosthenes theorem. Well, the last topic for the semester is roots. Call it nth roots, complex numbers. Right, in algebra, you want arithmetic, you want powers, and you want roots. You do other things actually too. For instance, logarithms and trig functions and all that kind of thing. There are trig functions of complex numbers. It gets complicated and you don't need it yet. So we'll save that for your complex variables class. In fact, logarithms are very interesting. They're infinite valued functions. If you take the logarithm of a number, complex number, you get an infinite number of values back. How about that? So it's complicated things like that, but engineers actually use those to get real results. They are important functions if you take complex variables class, or you'll see them in applied mathematics classes. So for this class, though, we at least, even though we don't do those special functions of complex numbers, we will do nth root of complex numbers. Well, at least finish the algebra of complex numbers, right? And how can we get those? Again, we apply Demosthenes theorem in reverse. I'm going to say consider, rather than writing out the formal method, I'd rather just demonstrate with an example. I think by the time I write out the general form, it's awkward until I do an example anyway. So here's 7a. Find the cube roots of minus 27 over 2 minus 27 square root 3 over 2i. Wonder what the cube roots of that complex number are. That's already a mess, right? But I can compute them using Demosthenes theorem. What do I need? Suppose if this is z, all right? Well, we can compute r for this one. We want to use polar form for powers and roots. What is r? It's the root sum square of these two numbers. Leave the I out, right? It's x squared plus y squared square root. Don't put in the I. Minus 27 square root 3 over 2 squared. If you run that on your calculator, it's kind of interesting. You can simplify it like this. Here's the algebra. Write it as 27 over 2 squared times 1 plus times 1 here plus or 3 over 2. So 1 squared plus square root of 3 over 2 squared here. There we go. So this times this gives this times this gives this. And now you can pull the 27 over 2 out. Right, the square root of the square undo each other. 1 plus square root of 3 over 2 squared. Well, this is, oops, not 1. Yeah, it's not square root of 3 over 2, it's square root of 3, I'm sorry. All right, this times this gives this. There we go. And let's see, this is 1 plus 3 is 4, square root is 2. 27 halves times 2 just gives 27. So r is equal to 27. This complex number is actually 27 units from the origin of the complex plane. That's part of its polar form. I also need theta, right? But I need the polar form to compute the roots. I really do. It's hard without it. Now I know that tangent theta equals y over x, minus 27 square root 3 over 2 over minus a half. Well, the minuses cancel and the 2's cancel, and I get, oops. This is 27 over 2, sorry. And I get square root 3. The 27's cancel also. Well, what is theta if it's tangent to square root 3? Remember how to do that? Solve tangent theta equal a number. Divide it as a quotient. Divide top and bottom by the root sum square, which is 2. Divide the square root 3 over 2 over a half, or you can put negative that, right? Minus square root 3 over 2 or minus a half. And which one do we want on the unit circle? Remember, for complex numbers, we want the angle that goes into the correct quadrant. This number here, if we plotted it, is x plus iy. X is negative 27 over 2. Y is minus 27 square root 3 over 2. This is way out in the third quadrant here. All right, here's your r and here's your theta. R equals 27, we just calculated. What's theta to go over here? Well, it must be in the quadrant 3, so we throw this one out, right? X and y are negative here. This is what we do. This is your y and your x on the unit circle. Y is minus square root 3 over 2. X is minus a half. I know this triangle, right? It's a 30, 60, 90. This angle, evidently, is 4 pi over 3, right? This one's pi over 3, the reference angle, 60 degrees. Pi plus pi over 3 is 4 pi over 3. All right, so now I've got my angle and my distance. Theta is 4 pi over 3. R is 27. And so I compute I guess I should say, the numbers such that R cosine plus I sine theta cubed is equal to this number here, 27 size 4 pi over 3. Right? Here's the angle, here's the distance. So we write the number that we want, get from the cube, like that. But there's one trick in this thing, and you have to do this. You say, actually, this is not the unique angle. I can add any 2k pi to this, right? So all polar forms for this complex number of these all go to the same point. If you compute cosine and sine of this angle, it's the same. So we want the number z, the number whose cube, r size theta whose cube is this number, the polar representation of z here. How can these things be equal? Well, remember by Nama's theorem, this is r cubed, r's cubed, and the angle is tripled. This formula. R cosine plus I sine theta to the nth power is r to the n cosine plus I sine of n theta. This was 4. I'm going to use that here with n equals 3 because I'm taking third power. It is r to the third cosine plus I sine 3 theta. So this is what I need to get cube roots. The numbers whose polar form is r size theta has to satisfy r cubed size 3 theta equals that. Well, now how can these be equal? We need r cubed equal, right? This is the r for this number, has to be the r for this number, and the angle for this number has to be the angle for this number. So we need r cubed equals 27 to find r, and 3 theta equals 4 pi over 3 plus 2k pi to find theta. Well, this is supposed to be a real number, right? R is the actual distance from the origin of the complex plane. It's real, and so it's theta. And so if R cubed is 27, that means R equals 3, the cube root of 27. And dividing this one by 3 gets theta equals, let's see, 4 pi over 9 plus this over 3, 2k pi over 3. And we have an infinite number of solutions, right? K equals 0, 1, minus 1, 2, minus 2, integers forever. There's an infinite number of solutions here, but when you think about it, actually every 3 values of k, after 3 values of k, it starts to repeat. All right, if I put k equals 3 here, then this becomes 2 pi added to this is the same direction as if I put k equals 0. This, right, this by itself with k equals 0, and k equals 3 just adds 2 pi to the value with k equals 0. It's the same direction. Same thing when k equals 1 here and k equals 4 here, it's the same direction. K equals 2 here and 5 here, it's the same direction. So actually k equals 0, 1, and 2 are the only different directions for theta. All the others are just coterminal angles. And so we'll say these are all the cube roots of the given number. R has to be 3 for all of them. They're all the same distance from the origin. And these 3 different angles, when k equals 0, 1, and 2, give 3 different directions. And that's it. Interestingly, we find out there's exactly 3 cube roots of this complex number. And that turns out to be true in general. If you want the nth roots of any complex numbers, there are exactly n of them. Kind of a neat result, right? It's like when you do, don't write this down, in algebra, x squared equals 1. What are the solutions? If you're looking for the number, the square roots of 1, well, it's x equals negative 1 or 1. These are the two numbers whose square is 1. If you want x to the 4th equals 1, though, what are the 4 numbers? If you figure it out with the same kind of thing here, you get 1 and minus 1, because the 4th power of those are 1, but also you get I and minus I. And there's 4 4th roots of 1. All 4 of these numbers, they're 4th power of 1. So, and in general, that's what happens. So we'll make this following note. There are in any case, always nth roots, values, let's say, of nth roots of a complex number z, including real numbers, because remember the real numbers are a subset of the complex numbers. Doesn't matter which number you pick, real or not real, there are always exactly n roots of it. And that's what we found here. When we took cube roots, we found 3 of them, right? That's like I write, suppose I want the square roots of 1. There's 2 of them, but if I want the square roots of minus 1, what are they? Well, I and minus I, both squared give minus 1. So there are always 2 complex roots, but even though this has no real solutions, it always has, when you want the square roots of minus 1 here, there's always 2 complex numbers that are solutions. They might be real, as in this case, or they might be imaginary, as in this case, so they might be partly real and partly imaginary, right? So that'll be the case. We'll always get n values for the nth roots of z. Cube roots, we get 3 of them. 4th roots, we get 4 of them, and so on. And here, let me give you the picture that I put up earlier and see if I can move this over now. Here's a good example. Suppose I want, it's like this one, cube roots. Suppose I want to find the cube roots of negative 1. In fact, let me move this over and I'll do this one as the next example. This will explain the geometry a little better. Example, cube roots, the 3rd roots of z equals negative 1. It's a real number that's also, you can think of this as negative 1 plus 0i. also a complex number. What are they? Well, for -1, right here, -1 plus 0i in the complex plane. What is the distance r from the origin? You can compute it as r equals square root of -1 squared plus 0 squared directly from the formula. X squared plus y squared square root is 1. Or how else could you have computed it from the picture? It's 1 unit from the origin, right? So you can look at it and see. You can do this calculation, or you can just look at it and see. What is the angle theta? You can compute it. Tangent theta equals y, 0 over x, -1, and say, oh, it's, in order to get tangent theta equals 0, it has to be 0 or pi. Which one goes in the right direction to this one? Oh, it's pi, right? You don't need to do the calculation. You can look at it and say, oh, it's 1 unit from the origin, r is 1. It's this angle pi in the complex plane. You just look at it, right? It's on the negative x-axis, so the angle's pi. So what we do is similarly in this problem, let's get this on the, is we want z cubed to get the cube roots equal r size theta for the number whose cube roots I'm trying to find. Well, z cubed by De Moivre's theorem is r cubed size 3 theta, where r and theta are the values for the polar form of the cube roots, equals r size theta for this one is r is 1, theta is, we want z cubed equal r size theta. And what you have to do here again is allow theta plus 2k pi, because these are all the same direction. But z cubed, let's put this down, is this number r1 cosine plus I sine pi plus 2k pi. There we go. So we want the cube of our roots to be equal to this, which is -1, right? It's just in its polar form. If you include the 2k pi, that's the trick in this, is if you include the 2k pi, then you find this. This is r cubed size 3 theta by De Moivre's theorem. Or, well, that means that r cubed has to be 1. R is real. What number cubed is 1? Only 1. And then 3 theta here has to be pi plus 2k pi. Right? Divide this by 3 and you get theta is pi over 3 plus 2k pi over 3. Or 2/3 pi times k, if you like. Now you see a very interesting result. The cube root is the cube root of the distance from the origin. Cube root of 1 is 1 still. Angle is 1/3 of the angle plus these values. Again, k equals 0, 1, and 2 gives you different directions. But k equals 3 is the same direction as k equals 0. K equals 4 is the same direction as k equals 2, 1, and so on. So there's only 3 different numbers you can get out of that. And so you get z 1/3 root is 1 times cosine plus I sine of pi over 3. That's with k equals 0. The second solution is 1 times cosine plus I sine with k equals 1 is pi over 3 plus 2 pi over 3 is pi. And the third one is z3 equals 1 times cosine plus I sine of this plus 2 is, let's see, it's 4 pi over 3 plus pi over 3 is 5 pi over 3. These are the polar forms, 3 of them, for the cube roots of -1. The 3 complex numbers, if you take their third power, give you -1. And here's why I put the picture up here. This is one of them, right? You take r equals 1 unit out and pi for the angle you get over here. That's that one. This one is actually -1. When pi is the angle and you're 1 unit out, you find out the cube root is -1. Now, if you compute this cosine plus I sine, what you'll get is 1 times cosine pi over 3 plus I sine pi over 3. Cosine is 1/2 and sine is square root of 3 over 2. So this gives you 1/2 plus I square root of 3 over 2. This number cubed is -1. This number cubed is -1. You already knew it. And then this one at 5 pi over 3 is 1 times cosine 5 pi over 3 plus I sine 5 pi over 3 is, let's see, 1/2 minus I times square root of 3 over 2, just using the unit circle. These are the 3 cube roots of -1. And you see them plotted here. There's something very geometrically beautiful. They're all in a circle whose radius is the cube root of the original number's distance out. So -1 was 1 unit out. These will all be the cube root of 1, or also 1 unit out. The angle of the first one will be 1/3 of the original angle. So the original angle is pi. The first one here will be pi over 3. And then they're equally spaced. So for cube roots, 3 equally spaced angles, beginning with 1/3 of the angle of the number whose cube who you want to get when you cube this. And it applies to higher numbers. If you want 4th roots, you take 1/4 of the original angle and put 4 equally spaced angles. 5th roots, you take 1/5 of the original angle. Take 5 of them around a circle whose radius is the 5th root of the original radius. And so these are very nice geometrically. They're always symmetrically spaced like that. And for nth roots, you always get n numbers. It's kind of difficult, but it's kind of fun too, I think so. But engineers use these in real life for getting good results in their problems. Any questions on that one? No questions? That's a hard one. All right, so I want to ask you higher than 3rd or 4th roots. I'll probably just ask you a 3rd root on the final. See if you can do those practice problems that I put on the practice exam. And I think you'll be able to do this with a little work. We'll review these next time. That's the end then. That's all the material for the course. I don't want to start something new. Okay. Anything you'd like to see in regards to this? You want to see another power or Heinecken polar form or something like that? Otherwise, I'll leave it there. I guess we can go slightly early today, huh? All right, we'll bring in lots of questions next time, and then the last lecture we'll review next time, and then the final is next week.